Okay, in this video we're going to continue with the problem of the previous video where we wrote node voltage expressions for each of these three unknown nodes, V1, V2, V3. So if you look back at the previous lecture, you can see the equations that we came up with. Now if you go ahead and solve those three equations, three unknowns, correctly, these are the answers. V1 is 80 volts, V2 negative 64 volts, and V3 156 volts. So now we're going to take these answers and find other circuit quantities for the element, such as voltage across the element, current for the element, and then once you have voltage and current, you can get power from V times I. So for example, we can find the current at this node V2. So I1, which is the current through the 3 ohm resistor, well, it's just going to be the voltage across the 3 ohm, which is the difference of V1 and V2. Okay, V1 minus V2, so that would be 80 minus 64 volts. That's the voltage across the 3 ohm resistor. Then to get current, you divide by its resistance 3. So 144 volts divided by 3, that's 48 amps. Okay, so there's 48 amps flowing through that 3 ohm resistor and flowing into V2. Now IX, IX is the current through the 4 ohm. That's going to be V2, which is minus 64 volts, minus 0, right? Because ground is 0, and that's the voltage on the bottom side of the 4 ohm, divided by 4. So you see IX comes out to minus 16 amps. Okay? And remember, a negative sign in front of a current means that the current's really flowing the other way. So see, when IX is defined as a current flowing down, it's negative. So that means that's the same as 16 amps flowing up. So you see, not only is the current through the 3 ohm flowing into node V2, but also this current flowing through the 4 ohm is actually flowing into node V2. Then also look at this, that the dependent current source value is 4Ix. So that's 4 times negative 16. That's minus 64 amps. Okay, and that's the same as showing the arrow of the dependent current source going the other direction with a positive 64 amps. Okay, so if you look at V2, what we have is we have I1 and I2 flowing in, okay, 48 and 16, and flowing out is the 4Ix. Okay, which when you show the current going the correct direction here, that's a positive amount. So 16, or excuse me, 48 plus 16 flowing in, 64 amps flowing out. So you see KCL is satisfied at that node. We could also look at the current through the 2 ohm resistor at the top of the circuit. Okay, that's going to be V1 minus V3 over 2. So V1 80 minus V3 156, that's a minus 76. Okay, so minus 76 volts divided by 2, that equals minus 38 amps. Okay, so that means I2 also, because the negative sign here, it means that I2 is really going, see, this negative 38 amps goes with when we have I2 defined this direction. Well, that's the same as saying it's plus 38 amps with I2 going the other direction. See, so I2 is really flowing right to left because it's going from the higher voltage end, which is on the right side, which is V3, 156 volts. It's flowing from 156 volts to 80 volts, because remember, through a resistor the current always flows from the higher potential end to the lower potential end. And then I think you can see that here at this node, 10 amps flowing in and 38 amps flowing in, and then we calculated I1 earlier, 48 amps flowing out. So you see KCL is satisfied here. Let's look at a loop here and see that KVL is satisfied. Here at the 10 amp source, the voltage across the 10 amp source that's just going to equal V1, right? Because one end of the 10 amp source is connected to V1, the other's to ground, and voltage at a node is with respect to ground. So that 80 volts, that's the voltage across these two nodes that the 10 volt current, or excuse me, the 10 amp current source is connected to. So the voltage across the 10 amp current source would just be 80 volts. Okay, and its polarity would be minus plus like this, right? Because 80 volts, of course, is greater than ground, so the higher voltage end would be on the top for the current source. And then if you look at the 3 ohm resistor, okay, the voltage across the 3 ohm resistor, well, that's right here. We calculated that to get the current for the 3 ohm resistor, so that's 144 volts. And the polarity was plus minus, where the higher voltage end is on the left side, right? Because 80 volts is higher than a negative 64 volts. And then the voltage across the 4 ohm, okay, well, that's just going to be, from Ohm's law, 4 times the current through it. So 4 times the current through, which was 16, so that's 64 volts. And then the polarity is going to be that the higher end of the voltage is on the bottom, right? Because 0 ground is higher than a negative voltage, right? Negative 64 volts. You know, we made an analogy in a previous class that, you know, you can think of voltages at nodes as heights on the surface of the earth. Well, when you have a positive voltage at a node, that's like so many feet above sea level. When you have a negative voltage at a node, that's like so many feet below sea level. So you see here, ground, just like sea level, is higher than, you know, a negative potential. And the polarity of the 64 volts would be that the plus is on the bottom and the minus is on top. So you see, when you go around this loop, this left loop here, you're going minus to plus 80 volts across the current source, then you're going plus to minus 144 volts across the 3 ohm resistor, and then you're going minus to plus across the 4 ohm resistor, 64. So you see the minus the pluses, the 80 plus the 64, equals the plus to minus voltage, the 144. So you see KVL is satisfied. And you could do KVL for any loop in this circuit. You know, we just did the left loop, but you know, I would recommend on your own, you know, do the KVL around this right loop, do the KVL around the outer loop, and again, just prove to yourself that you know, these Kirchhoff's laws, the voltage law and the current law, that they're always satisfied. So maybe we'll just finish here with calculating a power. Like let's find the power for the dependent source. Okay, well, power is V times I, as we know, and we came up with the current for the dependent source at 64 amps. Okay, so 64 amps for current. Okay, and the voltage across that dependent source is just the difference between V2 and V3. So we have V3, Okay, this is voltage for the dependent source. Okay, we have V3 at 156 minus V2, which is at minus 64. So that gives us what? That comes out to 220, if I did my math right here. 220 volts. Right, because 4 plus 156 is 60, and then add 60 to that, 220. Okay, so 64 times 220 volts. Okay, which is quite a bit of watts. Let's bring up the calculator here. See, 64 times 220. Okay, so yeah, 14,080 watts. That's our answer here. 14,080 and then watts. Okay, that's how much power we have for the dependent power source or dependent current source. And then you should be able also to determine whether that dependent source is supplying or absorbing power. And remember, to determine that, we have to look at the direction of the current at the higher end voltage side of the source. So V3, remember, is 156 volts above ground. V2 is minus 64 volts above ground. So this is the higher voltage end of that 220. And remember that, as we saw earlier, the current is really flowing out from left to right. Okay, this is the real direction, right? Because remember, when we show the current going right to left of the dependent source, that's a negative current. So see, if you put the polarity down here, you can see that that dependent source is supplying power, that the current is leaving the higher voltage end. Okay, so this was another example where we achieved our answers through no voltage method, but then once we have the answers, as we did here, we're using things we learned prior to node voltage method, Ohm's law, KVL, KCL, you know, what we learned about power being absorbed and power being supplied by looking at the direction of the current at the higher voltage end of the element. All those things we're using you know, in these problems. So again, you can't forget all the fundamentals that we learned at the beginning of the quarter, even though you're learning this new method called node voltage method. And you know, again, that's for the rest of the quarter. There's going to be a method after node voltage method called mesh current method, and then we're going to get into you know, something called superposition and equivalent circuits. And no matter how fancy the topic, all the fundamentals are the same. So it's really important to get a good handle on these fundamentals.